All right, welcome back, everyone. So today we're going to talk about solving systems of linear equations with two variables. In this section, you're going to learn the definition of a system of equations, how to solve a system of equations with two variables, and how to set up and solve a system of equations given a real-world problem. So a system of equations is a collection of more than one equation with more than one variable, more than one unknown. Systems of equations are useful when there are more than one variable. Now, every system needs to have as many equations as it does variables in order for you to be able to solve for all of them. So if you have two variables, you need two equations. If you have three variables, you need three equations. And now there are three methods to solving a system of equations, but we're only going to talk about one, and that one is elimination. Right? Elimination is the easiest method and it's the most useful. So that's what we're going to focus on. To solve a system using elimination, we want to add both equations together so that one of the variables adds to zero. This may or may not require multiplying one or both of the equations by a constant. Once you've done that, you'll solve for one variable, the one that's remaining, the one you didn't eliminate, and then use one of the original equations to solve for the second variable. When we're talking about systems with two variables, your answer should be written as an ordered pair, x and y. So it's going to be a point. If the solution to that system exists, we say that it's consistent. If the solution is unique, we say that it's independent. And so systems can have three possible outcomes. You can either have two lines that cross each other and meet at one point. So it has exactly one solution, and that solution is unique. So it's consistent and independent. We can have two parallel lines that never cross each other. And since they never cross, there's no solution. And so if there's no solution, then the system is inconsistent. However, that no solution is still unique. And so it's inconsistent, but it's also independent. And finally, we can have two lines that are identical, two that sit right on top of each other. And so every point is a solution. Right? So there is a solution, so it's consistent, but there is no unique solution because there's an infinite number of them. And so the solutions are dependent. So let's first practice by solving the system of equations, and then we're going to determine whether it's consistent or inconsistent, dependent or independent. So we have 2x plus y equals 2, and x minus y is equal to 7. We want to solve this thing by elimination. And to eliminate, we're going to add the left-hand side of each equation together and the right-hand side of each equation together with the intent to eliminate one of the variables. We want the coefficients of one of the variables to add to 0. So in this case, if we add straight down here, right, then 2x plus x is going to give us 3x. Positive 1y minus 1y, well, positive 1 minus 1, that's going to give us 0. And then 2 plus 7 is 9. So we've now eliminated y. And what we're left with is 3x is equal to 9. We then divide by 3. We get x equals 3. We can then take x equals 3, plug it back into any of the other equations, and solve for y. So we have 2x plus y is equal to 2. If we know x is 3, then we can solve for y, just subtract 6 from both sides. We get y equals negative 4. X equals 3, y equals negative 4. Our ordered pair is going to be x comma y, which is 3 and negative 4. That's how you should input your solution. So because we have one solution, one unique solution, the system is consistent, And because the solution is unique, it's independent. Let's try another example. We have x minus 3y is equal to 2. And 6x plus 5y is equal to negative 34. It doesn't matter which variable we choose to eliminate, so always do whatever it takes to make it easiest on us. If we want to eliminate y in this equation, then we've got to multiply these equations by numbers so that y adds to 0. If we want to eliminate x, we would have to do the same thing. But there being a coefficient of 1 in front of x means that it's easier to eliminate x. So let's do that. We want x to add to 0. We have positive 6 on the bottom. And so we want to multiply the top equation by negative 6. And that's every term. So what we're going to get now for our system, negative 6x plus 18y is equal to negative 12. And then we can just rewrite the second equation. Now we can eliminate it. We just add straight down. Negative 6x plus 6x is 0. 18 plus 5 is 23y. And that's going to be equal to negative 46. If we divide both sides by 23, we'll then get y equals negative 2. We can now go back to one of our original equations, x minus 3y equals 2. And since we know that y equals negative 2, we're just going to plug that in. X minus 3 times negative 2 is equal to 2. So x plus 6 is equal to 2. If we subtract 6 from both sides, we get x equals negative 4. And so our solution, negative 4 and negative 2. And once again, because it exists, because we have an answer, it's consistent. And because it's unique, it's independent. Okay, we're going to just try this again. So we've got 4x minus 2y equals 3. And we have 2x minus y equals 4. Let's eliminate x. So to do that, we can multiply the bottom equation by negative 2. And what we'll get is 4x minus 2y equals 3. And on the bottom, we get negative 4x plus 2y equals negative 8. Now, when we eliminate, 4x minus 4x goes to 0. Negative 2y plus 2y goes to 0. And 3 plus negative 8 is negative 5. So we're left with 0 equals negative 5. This is obviously not a true statement. And because this thing didn't work out, we got something that wasn't true, 0 equals negative 5. Then that implies that this system has no solution. And if the system has no solution, then it's inconsistent. But having no solution is unique, so it's also independent. So finally, we can use systems of equations to solve some real-world problems. So in this example, we're going to set up the system based on the information, and then we're going to use it to answer the question. So a mail order equipment business shipped 120 packages in one day. Customers are charged $3.50 for standard delivery and $7.50 for express delivery. The total shipping charges were $596. We want to know how many of each kind of package was shipped. So first of all, let's assign variables to the things we're trying to learn. Let's say that X is our standard delivery, and y is our express. So now that we've got letters assigned to these things, we're trying to figure out the number of each one. So we want to solve for x and y. We've got some information we need to pick out from the problem. First of all, it says that they shipped 120 packages in one day, which means the total shipped, the total amount, x plus y, should equal 120. So we get one equation from just the total amount. How many did you sell of each one? We can get a second equation from the cost. We know that for every x they sold, or they shipped, it costs $3.50, so 3.5 times x. For every express they sold, it was $7.50, so 7.5 times y. And that's got to equal the total amount of money, which is $596. We can now use elimination to solve for one variable, and then use the equations to solve for another. So let's multiply the top equation by negative 3.5. And what we get is negative 3.5x plus negative 3.5y is equal to negative 3.5 times 120, which is negative 420. On the bottom, we just rewrite the equation, 3.5x plus 7.5y is 596. And now we solve by elimination. When we add straight down, the x's cancel. Negative 3.5y plus 7.5y is just going to give you 4y equals negative 420 plus 596 is going to be 176. Divide by 4. And you get y equals 44. So we know they delivered 44 express packages. Well, if we know they delivered 120 total, and 44 were express, then x should just be 120 minus 44, which is 76. And so notice when you're setting up this system, you want one equation based on the total amount, the number of each one, and then you want another equation based on the cost of each one, how it adds to the total cost. So at the end of the section, you should be able to solve a system of equations with two variables, and then set up and solve a system based on a real-life application.